Welcome to another very interesting panel session or perspective session. I think this is one of the most interesting topics that we have today. It's 3D printing in serial production, how to get there. And today with me on stage, I would like to introduce Dr. Jan Sander. He's expert for additive technology at Brose Fahrzeugteile. And he will start with his presentation on series production of metal parts in the automotive industry. And also with me on stage, there is René Mücke, manager engineering and plant manager Markkleeberg at Straumanngroup. And with him, Karsten Müller, director business development at RapidShape. And they will later have also a presentation on Dr. Smile, Straumann and RapidShape partnership, how to print 10,000 individual aligner per day. So enjoy the session.
Thank you very much for your introduction. So today I want to tell you about our journey into serial production from the viewpoint of an automotive supplier. So first of all, let me introduce Brose to you, because probably you don't know our company well. So Brose is a tier 1 supplier, for example, car seats, for door modules, for window regulators, for electrical engines. So every engine in a car that moves something except the engine that drives the car. So only components around that. We are quite big. In every second car that is produced worldwide, there is at least one Brose product, which means that everyone here in this room has certainly experience hands-on with the Brose product, but probably you are not aware of it, because all our products, as you see, are hidden. The company is quite huge. We have 30,000 employees and a turnover of 7.4 billion euros. And inside of this large company, we have a team of 15 people dedicated to additive technologies. And we are separated in two functions. One function is a central function. This means that we set all the standards for 3D printing worldwide for the Brose Group. We do all the trainings, we develop the materials, we develop the processes, and we design the parts. And as a second function, we are a pre-production. So in the same way that Brose has its own stamping plant or its own injection molding plant, we have a 3D printing plant. And this 3D printing plant is providing parts for Brose internally, but also for external customers. We are producing prototypes, we are producing production equipment, we are producing spare parts, and we are also producing serial products. And today I want to guide you to the different steps that we had to take to get there, to the serial products, because we have some very special things to consider in an automotive world. So first of all, what we need is system compatibility. And the automotive world is already there, it is established. We have standards that we need to apply to, we have quality guidelines that we need to apply to, we have special materials, we have special production and assembly processes. We need to fit into this already existing system. Second, what's very important for us is that we are cost effective. We have two main reasons, especially for our department, for this. First of all, our department is not even allowed to calculate their own prices. If I have to offer a part, the price of my part is calculated by central controlling of our plant. So I can just give in input, but I have no control about the cost. And the second factor is that even though we are an internal supplier, we have to offer our parts on a bidding platform. So the purchasing departments are buying the parts from this platform, and everyone is bidding on this platform, also external suppliers. And usually, until now, the way was we bid an additive part, and the external supplier usually bids a part which is produced conventionally. And the buyer will always pick the cheaper part. So if we don't have the best offer, the part will not be 3D printed. There is no advantage, no bonus for us as an internal supplier. So we have to be better. And only if we can get through these 2 points, we can get to the application benefits that we heard the last 2 days so much about. For us in the automotive world, this is a sad reality, but it's not worth money. We can't get more money for a part just because we have a better function or because it's lighter or whatever. The purchasing guy will always choose the cheapest option. So let's go through the 3 steps and see what we had to do there. So first of all, compatibility with the system that we already have. The automotive standards to apply to these as an automotive supplier it's a task that you have to fulfill, but for us it's very much manageable. So we can pick this up. Second of all, the quality guidelines, this is also established. We just need to apply to these. The first big hurdle that we saw for us was in the compatibility with the production and assembly process, and especially regarding the materials. If we look at an example here of a seat structure, the seat structure is built in a very specific way. It is mostly built up out of stamped parts, and these stamped parts are then, after stamping, welded, cleaned, and coated. All these stamped parts are made from low alloy sheet metal steels, and in the AAM world, usually what we have is tooled steels or low or high alloyed corrosion-resistant steels. Those steels will never fit into the production process that we have. So even if we could make a part which is better, lighter, and cheaper, we would never bring this part into a seat structure, because nobody would weld it to a seat structure, nobody would clean it because it's not compatible, and nobody would do the surface treatment that we are used to. So what we did is we developed our own steel. We made an alloy development for a sheet metal steel, which out of 3D printing has the same properties as the sheet metal according to the norm of a sheet metal. So this means we have the same chemical composition, this means we have the same mechanical properties, we even have the same faces in the steel. The only difference that we have is in the face arrangement, because of course we don't have a rolling texture in our part, we have a 3D printing texture. But luckily for us, in the norm of the sheet metal steel, there is only a bigger amount of a certain texture forbidden. Since we don't have a texture, we can never go above this amount. To prove that it's really the same, the material, not only according to the norm, which is only static properties, we also made intensive crash testing. So what you can see here is crash-tested seat rails. So the seat rails are the part that are connecting your seat to the bottom of your car. So this is a highly loaded part in a crash situation, and therefore one of the most and well understood parts that we have in the Brose company at all. And we could show here, you can see always a picture of the 3D printed part after crash testing and the picture of the original part after crash testing, that even under dynamic load, we have the same mechanical properties. And this all combined with the system compatibility with our production system. And we did this is just an example, not only for the sheet metal steel, we also did it for low alloyed hardenable steel. So we also print with the preferred hardenable steel that we use, for example, for gearing parts. We also do this for aluminum die casting alloys, for example, ALSE9 CO3 or ALSE12 as alloys that we applied to the 3D printing process. And we also do this for pure copper, which, for example, we need in our drive systems. And the same thing, the same strategy we also have for polymers. So in polymers, we have also the polymers that we know from injection molding. So we have, for example, the PA6 with 30% glass content. We have a POM, we have a PP, and so on. So the whole strategy behind this is to be compatible with the production system that we have, because otherwise we can change the system. It's already there, it is established. A huge company is behind this, and behind the huge company is a huge industry. It's the whole automotive industry. You won't change this for an AM part. And the second step that we need to do is to bring the costs of the process down. So yesterday we had a very nice talk from BMW who showed what you need to do regarding design of AM parts, and we can support this fully. We have exactly the same findings. Even though we have this huge freedom of design in our parts, in theory, and also for prototypes in reality, we cannot use this freedom of design for serial production. We need to design for cheap and cost-effective parts. So we need a very specific design language for serial production of AM parts. We lose some of this freedom on this journey. The second step that you need to do is we need to optimize the printing process itself. So, for example, we have specific parameter sets for every serial product that we have. There is not two products that share the same parameter sets, because everything is optimized to the absolute limit. You can see here on the picture in the middle, on this little sand, a very small part. So, for example, just in this small part, we have 16 different sets of parameters, so 16 different combinations of laser power, of scan speed, of hatching, and so on, to make the production of this pass as fast as possible, because we need to bring down the time that the machine is running, to bring down the costs. And go on with this part as an example. Also in the post-process, we can't afford any manual labor. It's just too expensive. So we need to do everything more or less in automated processes. We use for this, for example, for this part EDM. So we cut it layer-wise in a zigzag pattern. Afterwards, we collect the parts in a little basket in the machine. Then we put it in a sandblasting drum, sandblasted again from the drum into a packaging, and that's it. We don't touch any single part in this process, and this is what makes it cost-effective. Here you can see an overview about our serial products. So at the moment, we have 4 million parts running as booked business in our serial production, and 200,000 parts we already have printed and delivered as serial production parts. And this is excluding prototypes and production equipment. And there is not one of these parts in there that is in any way more expensive than the conventional counterpart. Otherwise, our purchasing guys would not have bought this. So the challenge is huge that we have to overcome here to really go into serial production with bigger numbers. So let me summarize. The system compatibility is something that is doable. We can apply to the standards, we can apply to the quality. Even if we need to develop new materials, we can do this, we can overcome this. We can become compatible with the system. Our biggest challenge is to be cost effective in the production. And this means that we need to do very extensive work regarding material prices, regarding the productivity of the machines, and regarding the costs of the post-process. And only then we will see all these benefits that we have from the AM. And we all know the benefits in our parts, because they need to be affordable. Or we need to find someone who's willing to pay more for a part that can do more, but usually you won't find these guys in the automotive industry. So we as Brose, we will continue to concentrate on the second step, to be cost effective, because if we are good there, then we can automatically apply all these benefits that we would have from additive technologies. Thank you very much.
Thank you very much. We will now hand over to a completely different industry, to Dr. Smile, and he will just explain what we can expect.
Yeah, ladies and gentlemen, welcome to our session. It's a pleasure for me to present with Karsten together as a partner, and we like to start with moving pictures directly. So we have a small intro for you from real production in Markkleeberg, production site in Markkleeberg, close to Leipzig. With the 3D printing technology, shortly for you, moving pictures. And I'd like to go ahead to introduce our partnership, Karsten here and me. We like to show you what we are doing in serious production of medical parts. And I have the very first one close to my heart, in my left pocket. So this is the very first one from Dr. Smile. We produced in our factory in Leipzig. Short introduction from myself. So I'm manager engineering and plant manager at Interim in Markkleeberg. I'm working with Straumann 14 years. July 1st was my 14th year starting, 15th year starting, and I'm diploma engineer and master of engineering. And I have a wonderful wife and 2 nice daughters. And soccer is, thanks a lot. Soccer is my hobby. And then I hand over to Karsten.
Thank you so much, René. So, hi together, Karsten Müller, Head of Business Development and Sales within Rapid Shape. I'm within Rapid Shape in the meanwhile for 4 years. but I grew up in the automotive industry, at least business-wise. So Stuttgart area, various functions in operations, in sales, in business development, in product management, etc., etc. I'm also educational-wise and double in engineering, and the hands were clapped for you, married too, with 2 children. Thank you. Speaking about Rapid Shape, not sure if everybody is aware about Rapid Shape, had heard the name and can allocate it. Rapid Shape is a printer manufacturing and development company located in southern Germany, close to the very beautiful northern border of the Black Forest. And what we can bring you today is a little bit the experience of various branches, how they became digital. So years back, the jewelry industry became digital. This was a phase like, I can feel it here too. So will it be the future? How could it be the future? In the meanwhile, in jewelry, 80–90% of all the productions of the samples and also of the serial productions are done in additive manufacturing. Same about hearing aid. 10 years, 12 years back, hearing aid thought about becoming digital. More than 80, up to 90% of the orthoplastics, the in-ear molds that are adapted to each human, are produced on additive manufacturing. Now the business case we present today, or we're going to present today, is a dental business case, and the dental brush is, we can argue if it's in the dipping point, sharp before the dipping point, or close after the dipping point. Dental industry becomes more and more digital. But to give you the opportunity to deep dive into the case, I want to hand back to René, because of René can give you an idea about who is the end customer, what are the needs, and how started it in a US-based Texas bar.
Exactly. Thanks, Karsten. So Together for Strong Solutions, so Straumanngroup, introduce it a little bit to you. So Straumanngroup, everybody knows, I think, and ClearCorrect is integrated to Straumann since 2017. And Dr. Smile, who is doing the direct-to-consumer business, is integrated in the Straumann business since 2020. And we are aligner manufacturing in Markkleeberg, close to Leipzig in Europe, with a aligner manufacturing center for ClearCorrect and Dr. Smile. And we're producing all Dr. Smile cases in Markkleeberg directly since 2020. So we're doing serious production since 3 years, in 12 steps to a final aligner. And Edcon is 100% Straumann daughter, or yes, 100% integrated. We are doing prosthetics and auto manufacturing close to Leipzig. If there's some volunteer to see it, we could collaborate afterwards. We have more than 9,000 square meters, and we have a mass production, and it's a special thing. Every part is different, right? Every part is looking different, and this sometimes leads to compromises we need to do. And yes, you see the brands on the right side. The vision to mission. We like to tell you the story, how we come together and how we start. So the first brainstorming was done between our both bosses in a Texas bar close to our US Texas plant, and they come together and work on a slide of pinches, right, and describe what could be the rough idea to manufacture aligners together with 3D printing technologies. And then our both bosses hand it over to us. What are the major requirements? And I like to introduce you the major requirements right now. So we like to have a high level of automation. We like to have nearly operator-free 3D system, 3D printing area. We like to have a resin with automatically filling. We also asked them the print time should be below 2 minutes per model. This was a strong requirement. And yes, the automatic separation of the models without human hands is number 5, and the strong number 6 is the automatic cleaning of the models. These requirements we gave to Rapid Shape as a very good partner, and then I describe right now how it runs roughly. So we Rapid Shape did with us together a sprint of 6 months to define the first pilot run lines. Then we did an FAT, SAT, and training sessions together, and then we started production in August 2020. So it was a very short time frame in 6 months to come to serious production. For sure, not everything is perfect when we start production, everybody knows. So we did a lot of continuous improvements directly, a hard time for us. But finally, we are very happy with the solution right now. And then we ramp up these lines globally in 4 continents. and continents. And with these requirements and this rough story, I hand over to Karsten. He will tell you how we did it. Yeah.
Rough requirements, tough requirements, born in a Texas bar. How together we solved it. I want to start a 1-minute video to give you the idea how the operation look like. This is the entire set of 15 printers sitting close together. We have integrated the software into the ERP system and also into the MES system of our client, so it's hand in hand. The refill pump you have seen, the printer is auto-rating in the print because of its DLP based. In the end of the print shop, it's automatically peeled off and transported automatically to the very next step. You can see here the conveyor system. It's fed in the centrifugal cleaning station. The uncured resin is fetched together in a box, could be reused, and in the end of the process, it's handed over in a buffer station to be allocated into the next processes. So all the requirements you mentioned, 2 minutes print cycle, hands-free, operator-free loading of the machines, hand-free unloading of the machine, resin refill, each and everything of these requirements is established in a serial production. Allow me now the next sentence. That is not a castle in the sky and the idea for the future that is running for years on high OEE levels in the meanwhile. Giving you a little bit more detail, the D100 is the printer itself that is based into the entire system. The entire build plate is roughly the shape of a letter paper. The height is absolutely fitting to dental models, but we could print up to 120 millimeters in the height with this kind of machine. And the machine itself is bundleable into an inline system. This is a full-flash modular system. You can run it with 1, 2, or 3 printers, but up to 5 printers. And in the production cell, you later on will introduce a little bit more in detail. We bundle up to the maximum of 5 printers and various of those lines in a production cell. Like I also said, it's not only about hardware, resin, and workflow. It's about also software integration. Imagine each and every arch is an individual STL file. We are handling gigabytes and terabytes of data each and every day because of each print shop is a separate STL file. We have a software hub here created that is able to handle STLs, is able to automatically nest, automatically slice. And to give you an idea, this is a fleet of computers that is slicing all day long and all night long too. We do have load balancing in between the various printers and the job monitoring, and the capability is scalable to multiple dozens of printers, dozens of slicing PCs, and dozens of various lines. But this is the theory. You want to have a much more detailed look into how the shop floor layout would be. René.
Right. So we like to show you how the production floor looks like. So we have the production cell concept is to do 10,000 aligners per day minimum, and we have many cells over the globe right now. We have a footprint of 500 square meters to produce the aligner in 12 steps, in 12 manufacturing steps. And at the moment, with this rapid shape lines, we are able to print 11,000 models per day. We have 2 operators for 15 printers, 1 operator to manage all the printing, refill, the bottles for the systems, and 1 operator who's handling the curing. We like to improve this. We have nice ideas. We show you later a little bit. And the printing time is below 2 minutes, and target is reached. And we still like to improve there as well. And we have a dual resin source concept, so we could work with many resins. For us, we're working with 2 resins, and this is very important with the supply chain, you know, from today. And you see the rough layout here, and you also see, in the next slide, how digital this production cell looks like. You know, we have the printers at the beginning, then we go to thermoforming, laser marking, trimming, touch-up, polishing, cleaning, quality control, packaging, sorting, and so on. And this is roughly the factory looks like, not in real pictures, but in simulation. And coming close to the end with the summary, what are the success factors? For sure, it's the partnership, to trust each other, having a high confidence to each other.
Suffering hard times when necessary.
Yes, it's also hard times, also problems occur. We need to fix within overnight, and this was tough, but we did it together as a team, and the collaboration hand in hand, we help each other, both sides, was really a key. And the success factor people we show you in the last slide is also people make the difference for sure. And yeah, this is another big success factor. We have serious ramp up in cooperation. So everywhere we start the production, USA and so on, other continents, we did it together, RapidShape and Straumann together to have a smooth possible ramp up with all problems, bug fixes at the beginning, which happens. And the continuous improvements is still a key to come to the point we have today, running constantly with a very high uptime, 11,000 models, 10,000 aligners per day. And Karsten, together we're sharing the team. I start with the Straumann on the top front. So we have Lukas Merklin, who starts with Andreas Schultheis, the idea, the Texas bar. And then we have our main engineers on the right side, Patrick Scherber, Marco Engler, who develop with RapidShape together the solution, doing all the FATs, SATs, bringing in ideas, improve the system. And me working together with Karsten to make it happen, also in tough times. And then I hand over to you for the RapidShape.
Thank you so much. It was a team on both sides. Much more people have been involved, but was a great collaboration. Like you can see here, engineering, sales, service, purchasing, quality, etc., etc. Allow me to sum up with the very last slide. René, we agreed on we will not stick what we have achieved. We will go on. And the next targets you handed over to me is increasing automation, increasing efficiency, increasing uptime, and decreasing labor costs, resin costs, and cycle times. Challenge accepted. We have tailored the concept together. And if you will follow what we have accepted or what we have addressed to, then we will be very close to the order for the very next 3.0 version level of the line. Looking forward to. Thank you.
Thank you very much for this interesting presentation as well. So we have seen two very impressive use cases of serial production in 3D printing. And let me maybe start a little bit by asking Jan again, do you see that there is a rise for AM applications in the automotive industry in general?
We definitely see it. So we heard a lot already from the automotive industry. Everyone is working on it, but it takes time. And it definitely takes a lot of effort on the cost perspective, because at least for the tier ones, maybe not so much for the OEMs, they're a little bit more free than we are. It is all about the costs.
Yeah.
So we need to be effective there.
I understand. So how far are we away from having a situation where the cost fits into the market needs or with high part numbers?
We saw massive improvements over the last years, mainly due to the developments that we did. And we see that this is going on, that we're not at the limit yet. So there will happen a lot from the projects that we have. We will see probably much higher numbers than we have shown today.
Yeah, super, thank you. Now coming to our cooperation example, it all sounds so successful and so easy, but I'm quite sure that you also have faced some challenges during the production ramp-up. Could you elaborate a little bit about these challenges that you have faced?
Yeah, I think the first challenge was to bring it from the slide of a pinch to a real project. This challenge we did together without big Lastenhefte, sorry, I'm missing the word in English, but without big Lastenhefte, just to basic specifications, requirements we did together, and trust and confidence. The second big challenge I see was the first line was delivered and not running, for sure, as always. But within sprint and a teamwork together, we bring it to production quite fast and adapt some things, I would say.
It's a total different story in running a printer once, twice, or 5 times, or running it 5 days a week, 24 hours a day. And this is not only idea, you run 3 shifts, 5 or 6 days a week, depending on the workload. And to train and to bring the labor force onto the level to fix minor topics. Imagine if you're head of operations in automotive, how the qualification level with your operators is to run an injection molding machine. This is not done by fingertip. These are experts and artists with their machines. And to transfer this knowledge into the labor force and also in the maintenance force to enable the partner to run it on OEE levels like required and like achieved, this was a challenge in ramp up. But not only in Markkleeberg in the plant, but also when we distributed the solution into the 4 countries or the 4 continents. In each and every plant, the ramp up was a hell of work, but we learned each and every time a little bit better for the next.
Yeah, I think that's a learning process, right?
And doing the ramp up together is very important, very close on site where it happens. This was a major key for the challenge.
May I ask, what is the current automation rate and effort of labor for the 3D printing processes?
Yeah, the automation rate is quite high, as we see, and we have usually this one operator if we exclude the curing, which we like to integrate in the future, and we will, I'm quite sure. It's one operator for 15 printers and the RSP software, handling exceptions, handling the daily stuff, the cleaning which is needed, not much, but it's needed. Not the yearly maintenance, but the daily or the weeklies which are needed. So one operator for 15 printers.
Wow. Yeah. Thank you. And of course.
Sorry to add.
Yeah, sorry.
In the meanwhile, we also reached levels of uptimes much higher than 90%, or is it a marketing number?
No, at the beginning we are much below, but right now we are between 92 and 97% uptime of the printers. We measure it every week.
Impressive. Yeah. Our audience is also asking, what is the failure rate? Having so many printers and high working time, how often and for how long do you have a failure? Maybe this is a very interesting question.
Yeah, if we're looking at the scrap rate of the models, we are around 2%. So 2% of the models are scrapped because we have a mass production of individual parts. So every part of this 10,000 is individual. So we have some compromises. And we really reduced it together with Rapid Shape, with all the know-how, to 2%. We are not satisfied yet, but 2% is the scrap rate for the models alone.
And to add here, the scrap rate is not only about printing, it's the entire value chain in production. So of course, sometimes the very last packaging step occurs a redo in the process change.
Yeah.
Okay.
Not everything related to Rapid Shape for sure.
Yeah. Can you also say something about the failure rates at Brose?
Ours is even below this 2%. If we have failure, then it's usually not after the printing process, but during the printing process. When there's some kind of problem with the printer, which is very nice for quality control because these parts are definitely scrap and it's very easy to separate them.
Okay, yeah, so easy to recognize.
Yeah.
Okay. Super, thank you. There's another question coming from the audience. How do you sort out the aligners? So it's going again to you for packaging after the manufacturing. So how do you do the sorting out?
Yeah, at the moment we have a quality control which is visible. So human beings deciding at the moment. We're also working for concepts to do it more automatically in the future. But at the moment, human beings with a quick check, visual points, bubbles, cracks, and so on.
And we had a lot of discussion with the various plants because of production philosophy. Currently, we are in the most of the plants in a chaotic way of organizing the models in sequence. So the models are printed first in, first printed. And in the end of line, there's a sorting station where the cases will be picked together because of normally a patient case is
between 20 and 40 aligners.
Absolutely.
One case between 20 and 40 aligners. And exactly, that's also a key. We're doing single piece. So every aligner goes single piece until the sorting station where we bring the case together.
Okay.
This helps us to have a very short cycle times through the line.
Yeah.
Below 1 day. Yeah.
Interesting. Yeah. There's one more question again, going into the direction of the aligners. What layer thickness do you use? 2 minutes of printing for model sounds extremely fast. Yeah. So can you answer this?
Yeah, we can answer this. So we are currently on a level of using for this application 100 micron of layer thickness. and the 2 minutes are calculated by the print time divided to the models that are printed in a separate print shop. So the current range is roughly 30, 35, 37 minutes in printing, divided by in between 17 to 24 models that are printed. So this is the average numbers, and by dividing print time of roughly 30 minutes by 20 models printed, this is the number.
Okay, thank you very much. Yeah, this is not a question really. Or can you answer this question for you as well? I mean,
I would not.
no,
This
that's
is
difficult to
IP.
say. Yeah, yeah. Okay. Another question in the audience. You mentioned that you print 11K of models, but produce 10K of clear aligners. So 1K of models are defected. Yeah, it's again about the scratch rate, right?
Yeah, the scrap rate, yeah, it's models and aligners, but 10,000 is the minimum we need to ship. Some days we ship 10,500, some days, 10,200, so it depends really on the total scrap. But the model scrap is 2%, and the other scrap is varying also on special features which are coming, cut out slits, bubbles on the aligners. They're coming more and more really special features which are challenging to produce.
For sure, yeah.
Unfortunately, this enables that the rapid shape system is seldomly the bottleneck in the entire process.
No, it's the first process and the most important at the beginning, but right now it's not a critical path anymore.
It's the capacity, so we are capable to produce 11,000 models by the need of 10,000 aligners a day.
To ship, yeah. Because we will lose some aligners between printing and...
Sure, yeah. So that makes the difference, right? The gap in the number.
Yeah.
There's another question. Printing molds for aligners, some use the resin printing and others use powder printing. What are the pros and cons from your perspective for each of these technologies?
Ryan, would you like? The big advantage in using a wet polymerization is the cycle time. Because in such a system, you are capable to have the very first aligner model in hand 30 minutes after starting the production. If you go in a powder bed production, the production lots are bigger, but also the cycle times when you can further process the very next ones is much higher. I cannot deep dive too much into total cost of ownerships, but I can say I have run a lot of total cost of ownership calculations with various customers around the globe. And due to the fact that I know that they ordered DLP machines in running through costs, I would humbly also assess here that DLP printing could have cost advantages.
Okay, what's your opinion on that?
So for aligners, for us, it's difficult to say, honestly.
Yeah, but maybe
for the automotive industry, we focus on the powder bed systems, because for serial production, this is more the material that we need. With this resin materials, you have a duroplastic, which you cannot recycle, which is not allowed in the automotive industry. And you have problems usually with the ductility and also with the UV stability. And with the powder bed-based systems, we can use the same thermoplastic polymers that we use in injection molding. And this is what our customers want to have. So for us, it's natural to go in this direction.
All right. Okay, thank you very much. Yeah, time is running out. Maybe future outlook. So we have seen this serious production now, examples. What will be the next step or the next challenges for the future from both of you?
So for us, it's definitely to develop the process further. We are developing new materials that are cheaper, and we also develop new ways to print faster. And this is very extensive to do this. You need to put in a lot of effort and a lot of knowledge, but it looks very promising.
Okay. Yeah, very positive. Yeah, thank you very much. What's your opinion on that?
Yeah, for us, Karsten mentioned it together, what we hand over, improve efficiencies, also improve the resin costs per model with the gram per model. We have nice ideas and really looking promising to make a next milestone together. And also the sustainability, how to bring the material in internal cycles or external cycles. Is there any voluntary to have models? Let me know afterwards. We have a lot. Yeah.
Super. Thank you very much also for this outlook, and thank you for your questions. And thank you also for your presentations in this panel. It was very interesting. Thank you very much.